Hello everyone, my name is Jeffrey Myers, and today I'm going to be sharing with you a presentation on learning how to get good, helping improve ourselves and others with machine learning. My mentor is Dr. Hongjin Wang, and to start I wanted to kind of give you an idea of different data. With machine learning we deal with a lot of data. Here we have two examples that are very simple, not too hard to figure out. X is an attribute, Y is a classifier on the left, A, B are attributes on the right, with Y being classifier. And here's another one. This one has three attributes and one classifier, Y. And you can see just by the visual representation, it's kind of hard to understand how the classification works. Typically with machine learning, we are using many attributes. We can also use multiple classifiers. Here we have three classifiers on the right, G1, G2, and G3. I'll kind of skim over what all of the attributes and classifiers mean later. But first let's talk about the actual classification model. So the classification model algorithm uses entropy, information gain, and ultimately decision tree. Entropy is used to measure the data purity or variance. With high entropy, we have a low level of purity and a high level of variance. So we really don't want that. We want the low entropy. We need to watch out for arbitrary attributes such as unique identifiers like account IDs. Because those can give us false entropy. And with information gain, we are measuring how much reduction in entropy will occur if we split the data on an attribute. So we want a high amount of information gain. And when we find that the highest information gain, we split the decision tree on that attribute. Now the decision tree is what the model is going to use to make predictions of new unclassified data. After splitting, entropy and information gain are recalculated for each unique value of the tree node attribute. So analyzing our data, it's important to do this because we want to know what kind of data we have. So the kinds of data we can have are nominal values, which are non-numeric values. We have numeric values, binary values, and within the numeric values we can have continuous or discrete. Within the nominal values we can have qualitative, hierarchical, or non-hierarchical values. And with numeric values they can also be quantitative, so like money. And we also want to look to see if we have multiple classifiers, and also how much data do we actually have. The more the better. Classification model algorithms work better if our data contains no continuous values and a relatively small number of unique values for any given attribute. We need a large volume of data and a reasonably even distribution of data across all classifications in order for the model to be accurate. Complete data for attributes and classifiers, so it's best if none of the data is missing. After looking at our data, we may want to manipulate that data. So we can convert data values from continuous to discrete because we don't want those continuous values. We want to convert a large number of unique quantitative values to smaller number of unique values ranges. So 1, 2, 3, 4, 5, 6 would be converted to 1 to 3 and 4 to 6 as an example. And we're going to do this for the hierarchical qualitative values as well, except that whenever we're dealing with the hierarchy, we want to maintain that hierarchy. So great, good, fair, bad would be converted to great and good, and fair and bad. Now with the non-hierarchical qualitative values, we don't have to worry about the hierarchy, but we do want to keep any logical relationship that they might have. So here we have yellow, green, blue, violet, red, and orange. The values I've created are yellow, blue, blue, red, red, yellow. And you'll notice green, violet, and orange are not included in those, but they can be represented like green with yellow, blue. Now, reducing the number of attributes and classifiers can also be very important. We may want to merge multiple related attributes to a single attribute, or multiple related classifiers to a single classifier. So we also want to remove arbitrary attributes like account ID or emails, because those can negatively impact our model. So the reasons for doing this is that there's simplicity, speed, and accuracy. Simplicity allows us to make sure that our algorithm can handle the data. If there's too many unique values, then entropy, information gain, they both can be very small numbers, and we really don't want that because our machine may not be able to store such small numbers. So making our data simpler also allows an increase in speed and accuracy. With the accuracy, we do sacrifice some precision by doing this. So here's the breakdown of our attributes in the data set. We have school, the student's sex, age, address, family size, the mother's education, father's education, etc. Here are more attributes that are contained in the dataset, and then these are the last 10 that the dataset contains. And here we have our classifiers that are in the dataset. As I said, there are 3. The first one is the first period grade, second is second period grade, and then the final grade. When we train our model, we want to make sure that we consider sampling, because data can be too big. In big data, it takes too much space, too much memory, and time. So here I show you a couple examples of sampling. One is random sampling, which is typically not very good, and we have sampling with maintaining standard deviation, which is much better. Because it's a better representation of the entire original data set. Now, with testing the model, we want to also consider sampling. We want samples that are proportionally representative of the training data, and the test data should not appear in the training data. So here are my resources. I've included my GitHub repository for the Python script that I'm going to be showing you. You may clone it, play with it. It is a prototype, so it's not very pretty. It might be difficult to read, but it is there if you are interested. So let me go ahead and demonstrate the machine. So here we are in my workspace at the terminal, and I will go ahead and execute the Python script. Here on this line you can see I've got the Python script name, and followed by the data file, which is going to be used to train the classification model, followed by the number of classifiers contained in the dataset. And what you'll see is output showing us when it's found a new leaf for the classification model or the decision tree. And it's going to take a little while, so I will be right back. Okay, so the script is finished. Took about 4 minutes. And here we're presented with a prompt asking us if we want to give it a test file to make predictions on. Let's say yes, and then I will give it the test file name. Doesn't take long, it's already finished with its predictions, so let's see. As you can tell, Over here on the left in the directory, you can see that it's generated 3 trees. It's actually one for each of the classifiers, and we'll take a look at the first one here. So the head node of the tree is actually the attribute that affects the outcome of the data set the most. And the deeper you go into this tree, the less impact the attribute has on the outcome, to the point where it doesn't actually need any more attributes to make a decision. This is the classifier that this tree is for. This is the attribute that it's split on. Here are the attributes values. If we go down here, here's the attribute that's split with its first value, and it's going to split, or it splits on this next attribute here with its values, and it just keeps going on and on like that. As you can see, the tree is quite large. There was a lot of data. So now we can look at the predictions that it made. So here on the right is the data set that we fed to the decision tree. The only exception is that the data set did not include the outcomes or the classifiers. So it had to make those predictions on its own. Here over on the left is the actual predictions. And you can see that the algorithm created ranges for each of these classifiers. And we can see up here, if we compare, it actually was able to predict all of the outcomes. And with that, I end my presentation and open up for questions.